Good afternoon. It's a pleasure for me to introduce you to the presentation of Market Equilibrium Analysis considering electric vehicle aggregators and wind power producers without storage capabilities by Oscar Andrés Díaz Caballero and Paulo Manuel de Oliveira de Jesús from Los Andes University in Bogotá, Colombia, and José María Yusta from Zaragoza University in Zaragoza, Spain. The following presentation will be divided as follows: introduction, motivation, background, method, study case, results, and conclusions. In the scope of the smart grids paradigm, we can identify that the ongoing power system modernization process is carried out applying four main drivers: energy matrix transformation by allocating large amounts of renewable energy, promoting electric mobility in order to substitute combustion engines in the transportation sector, widespread deployment of smart meters in order to apply demand response programs, and the deployment of advanced metering infrastructure that enables the application of real-time pricing schemes to market agents due to their impact on energy losses and congestion. Electric mobility has important energy storage capabilities that intermittent generating plants do not have. Thus, electric vehicle aggregators can provide capacity and energy as virtual power producers by exploiting business opportunities, trading part of the stored energy in the plug-in vehicles in the wholesale electricity market. Smart metering can enable sending energy prices to elastic consumers under a real-time basis. Under advanced smart grid paradigm with telemetry based upon phasor measurement units, distribution management systems applications such as state estimation and optimal power flow are capable to compute locational marginal prices and send them to market agents. These LMPs penalize or reward the impact of all power injection on overall losses and line congestion depending on location. Using smart metering capabilities, the LMPs become elastic, which encourages intermittent power injection managed by aggregators. The research question raised here is how to evaluate market when demands on producers with storage capabilities such as EVs, producers with and without storage capabilities such as PV generating plants, and fault elastic demands with AMIs exposed to LMPs are duly included in the formulation of the complete alternating current AC optimal power flow. In this paper, two economic equilibrium models are studied in detail. First, we analyze the perfect competition solution driven by a benevolent planner in which real and reactive power dispatches, as well as the battery charge or discharge schedule, aims to maximize the global social welfare. Secondly, we address the monopoly solution where the total profit of EV aggregators and renewable generators are maximized considering that both producers belong to the same firm. In this presentation, we will show you that if only one firm runs PV, EV, and wind power injections, the firm might take advantage of the resulting LMPs in order to increase its own profit. But resulting dispatch is far from the perfect competition solution, jeopardizing the system performance. Literature about theoretical market equilibrium models in electrical power systems is vast. We can identify a number of theoretical models that incorporate four key aspects in the AC optimal power flow: the storage capabilities of the EVs, reactive response of intermittent producers, network constraints, and elastic demands. This table shows relevant contributions listed considering these key aspects. No contribution is found that encompasses the four above mentioned aspects and provides us a whole picture. This paper aims to fulfill the research gap. Locational marginal prices can be sent to consumers' smart meters at given node I under a day-ahead or real-time basis. Under this paradigm, higher prices lead to lower power consumption. Lower prices lead to higher power consumption. The demand curve follows the mathematical relationship stated in the first equation. The cost that a producer would incur is represented in the second nonlinear function. Finally, the social welfare for any bus I is shown in the third equation. The following optimization problem describes the perfect competition equilibrium, where the social welfare is maximized subject to the network constraints. This is the first model that is going to be analyzed. On the other hand, This optimization problem describes the monopoly equilibrium, where the producer revenues are maximized subject to the network constraints. This is the second model that is going to be analyzed. The proposed analysis was applied for illustration purposes in a simple 69 kilovolts 3-bus system as shown in the figure. The spot market node is set at bus 1. It will be used as the slack node for the simulation and provides the base marginal price or system lambda. A 10 megawatts wind power producer without storage facilities and an elastic demand is connected at bus 2. It has unidirectional active power flow for the generator and elastic demand. At bus 3, an elastic load and an EV aggregator are connected. For the elastic demands, the inelastic curves from the first figure were converted to elastic by creating a power-price relationship that mimics the original behavior. The resulting curves are shown in the second figure. For the power flow constraints, the values shown in this table were used. These values define the battery and generator's behavior. The first figure shows the hourly losses for the system in perfect competition condition, while the second shows the system in the monopoly conditions. As you can see, the total losses for the monopoly conditions are considerably higher than the perfect competition, being 8.46 per unit. The system voltages for the two scenarios are consistent with the system losses, showing a voltage very close to 1 per unit in the perfect competition, while oscillating between 1 per unit and the minimum in the monopoly scenario. The locational marginal prices that result from the optimization problems are shown here. It's interesting to see that the prices in the monopoly solution are very low when the batteries are charging and very high when they are discharging, maximizing the aggregator's profit. The injected power for each node shows the generated or absorbed power by the EV aggregator, the PV panels, and the slack node. While the perfect competition solution shows a balanced power flow, the monopoly solution is quite erratic, which at the end causes the increase in system losses. These figures show the demand behavior in each scenario. Since the demand are elastic, they respond to the change in prices induced by the aggregator in the system. The battery state of charge indicates how the battery is being used in the 24 hours period. In the perfect competition solution, the battery is being used to reduce the system losses, while in the monopoly solution is being charged and discharged as many times as possible to increase the aggregator's profit. The results of the optimization processes are shown in the following table. In terms of social welfare, we can see a huge detriment caused by the maximization of profit in the second scenario. Meanwhile, the profit for pi 2 plus pi 3 is considerably higher in the monopoly solution. The final table summarizes the most important results of the optimization, where we can see the differences between both of the approaches. Comparing the monopoly solution with the perfect competition solution, we see a decrease of $9,727 per day in social welfare and an increase of $679 per day in producer's profit. We conclude that under perfect competition, overall efficiency is achieved. Nevertheless, if EVs and wind aggregators are managed by only one firm, the power market is obtained by manipulating the reactive power output and the state of charge of the battery in order to increase losses, locational marginal prices, and therefore profits of the monopoly. In this case, system efficiency is clearly deteriorated. Thank you very much for your attention.